Okay, back here at the chemical reaction, and we've got our 6 mils of 6 molar hydrochloric acid, and as always I'm labeling everything, so we're keeping track of what we've got here. And I'm putting my labels on the back side of where my volumetric marks are, and we're going to be transferring this just by pipette. And we're going to use a long stem pipette. I'm going to move the top clamp out of my way so that I can go straight down the neck of the container here. And remember, this is a dropwise addition. We're careful that we don't add this too quickly because it is extremely, or can be extremely exothermic. We're not seeing a whole lot happening. We will in a minute. What I'm going to do is, now that I've added that material, I'm just going to give it a little bit of sort of manual stirring. And in fact, what I may do is to actually disconnect it and to give it a little bit of stirring by hand. Okay, let's add a little bit more. There, the spin vane is going. That's really what I needed, is I needed that spin vane to get going. And what I'll do now is, now that that spin vane is going, let's see if I can zoom you back in so you can see what happens with this. All right, you might see a little bit of reflux as this goes. We'll turn the spinner down a little bit. You might see a little bit of boiling as this goes forward. We need to control the rate so that we don't add it too quickly. And as we add it, the entire system should go biphasic and should clear. And we should end with 2 clear and colorless layers. Now what's happening is we're protonating the alkoxide ion. The molecule, or the species, is transitioning from ionic to molecular. As it goes from ionic to molecular, the molecular becomes soluble in the diethyl ether. And so that's why the system clarifies. Now we have a solid buildup here. I'm going to increase the stirring to try to get efficient mixing between the 2 layers. And that solid should break up. Now if we need to, in order to make this come out into 2 clear and colorless layers, we can add a little bit of water, or we can add a little bit of diethyl ether in order to make 2 good layers, as needed. More water and more ether will not hurt at this point. interestingly, that big chunk of solid that's in there doesn't normally happen. Let's take, and we'll open it, and we'll break up that solid, and then we'll put it back and let it finish going. Sometimes when great big chunks of things get in the reaction, it's just hard for them to break up and dissolve the way that they're supposed to. So a little bit of help at that point is appropriate. It doesn't take a lot, just to break it up. We'll reconnect, and we'll let the spin vane do the rest of the work. All right, we'll let this go for a little bit, and then we'll check back in with it. Well, I've had it mixing for a little bit now, and I've added just a little bit more of diethyl ether, and I'm going to slow down the spin vane. We're getting pretty good vortexing in there, but let's slow down the spin vane and show what this looks like. Now what you see in there is one thing that is floating in the middle at the meniscus between the diethyl ether and the aqueous layer on the bottom. And it's actually producing some little bubbles. And it's probably just a little bit of magnesium that happens to be in there. That magnesium is producing a little bit of hydrogen gas. We're going to continue to stir this until all that bubbling ceases, and I've got just two clear and colorless layers. Well, the top layer is going to be a little bit yellow, but mostly clear. And in the meantime, we'll get a separatory funnel and ring stand set up and show how we do all of that. We're set up here to do the extraction now. Now that we've got two layers, an organic layer and an aqueous layer, we're going to put them into the separatory funnel, and we're going to extract the organic layer, which contains the triphenylmethanol that we are going to isolate. Now, to set this up, we've got a ring stand. The ring stand's pushed back behind us for the base so that it's out of the way, so I have a clear, flat base where nothing's going to fall off it. I've got my 50 ml Erlenmeyer flasks labeled aqueous, organic, and this one is for the dry organic that I'm going to use in a few minutes. I've got my saturated sodium chloride solution, which I'm going to use as a pre-drying step. And there's one more thing that I need. I need 5 mils of diethyl ether. I'll have to get that in a second. And this guy's a magnet. There is a spin vane in the bottom of our round bottom. And if that spin vane were to fall into the circulatory funnel, then the spin vane could get stuck in the circulatory funnel and cause a problem. So what we're going to do is we're going to use the magnet not to remove the spin vane, but to retain the spin vane. So what we'll do is we'll take the drying tube off, we put the magnet in the palm of our hand, and then with the magnet in the palm of our hand, we'll take and we'll introduce the contents to the separatory funnel. Now the magnet retains the spin vane, so the spin vane is still inside here. Now you can see that there is material that is still inside this flask. We're going to police that material. We're going to add a little bit of water to this, a little bit of diethyl ether to this. We'll add them both into the separatory funnel before we do the extraction. All right, so I've got two clear layers now. I've policed the round bottom. The round bottom no longer has any solid residue in it. I've got 5 mils of diethyl ether to do my second extraction with. I've got the aqueous vessel queued up, the organic, and then one for me to use later on when I'm ready to decant. And what I'm going to do is I'm just going to mix this really quick. even though it's been mixing, I policed it, and I want to make sure that the two layers that are here get efficiently mixed. So what I'm going to do is I'm going to turn it upside down. I'm holding the stopper with my hand pressed in tightly. I'm going to let out any gas that may have formed. Gas forms when you're mixing aqueous and diethyl ether, well, actually aqueous and any organic solvent that is fairly volatile. The gas forms from the heat of mixing. The heat of mixing of the two solutions causes vaporization of the diethyl ether, and that vapor needs to be released or it will build up, and bad things happen when pressure builds up inside of vessels. So we continue to release that pressure until there is no more pressure buildup. We'll return the separatory funnel to its location. You can see that we've got two nice, beautiful, clear layers. And now what we're going to do is drain out the lower aqueous layer. The upper sort of yellowish layer is the organic. We're going to remove the stopper. The stopper is designed appropriately to be grabbed with the back of the hand. You grab it with the back of the hand so that you can still manipulate things and do things with your hand without setting this down on the tabletop. This can then be returned to the vessel anytime, and that way it never gets dirty, never gets anything stuck in the ground glass joint, and the ground glass joint should not leak. We will drain out the contents. I'm going to find a way to hold it so that the camera can still see it. As we get close to the end, we slow it down. Actually, we will take just a little bit of the organic layer there too. We'll switch out the flasks, put the organic flask in, and let it all drain out. Okay, now that we've done that, the next step is to put the aqueous back in and to re-extract the aqueous with 5 mils of clean, fresh diethyl ether. Notice that this does not take long to do, but this is a fairly quick process of extraction. Most students will labor over extraction, take forever to do extraction. It actually is a fairly quick thing. Okay, so now I'll take the organic back out. We'll put the aqueous back under here because that's the first thing that's going to come out of the set funnel. We'll put the lid back in, and we shake and vent. Before we even do a first shake, we vent it, shake it a few times, turn it upside down, vent. Always venting through the stopcock. You vent through the stopcock because if you try to vent through the larger ground glass joint, you wind up introducing contaminants into the joint, and then the joint will not seal properly, and it will leak when you invert the funnel. Okay, we're not getting any more gas. That means that we can just mix as much as we desire. The heat of mixing has been evolved. And now we'll stand it up and we'll let it clear. It'll start out turbid. The turbidity are the bubbles of organic and aqueous all mixed together. They'll separate based on their densities and polarities. Diethyl ether is on top, being 0.7 grams per milliliter. Water, being 1.0, is at the bottom. Remove the stopper. Drain out the bottom aqueous layer. Swap the flasks. Drain out the organic. Okay, now this time the organic goes back in, and we're going to do our pre-drying step. This is where we use the saturated sodium chloride in order to pull out some water out of the diethyl ether. So to do this, we add about 5 mils of saturated sodium chloride. We don't torture ourselves over the amount. We just sort of eyeball it. Lid back on. Notice I have not set the lid down on the table at any point. We vent, shake, vent, we want good, efficient mixing. The mixing is dependent upon the surface area. If you don't mix it, the extraction only happens at the interface, which is very little surface area interaction. It will not efficiently extract. So you need to get good, good surface area and efficient mixing by really pretty vigorously mixing it. All right, we need to get the right flasks in the right places. The aqueous is going to come out first. You can see that these two layers clear very nicely. So I've got a very sharp now aqueous layer and a very sharp organic layer. We'll drain out that aqueous. And the aqueous is just going into waste. So combining all the aqueous layers are fine. There's nothing in the aqueous layer that I want. And then we'll capture that organic layer. And we're ready for the next drying step. Now this is something I try to explain to students all the time, and it's a little difficult to show. We'll see if I can show it on camera here. I've got it zoomed in pretty tight. And what you can see are droplets that are adhering to the glass. You see those droplets adhering to the glass? Those droplets are water. The only thing that sticks to glass like that is water. Organic solvents don't do that. When you see visible water like that, that water is too much for the mag sulfate to be able to draw out, to be able to dry this entirely. And so what we're going to do is we're going to decant this vessel into this clean dry one. We'll do that decant step. We'll leave all that water behind, and we won't get any water in this one. So usually I would do this in the fume hood. Let's see if I can do it on camera just to show you what that decant step looks like. We pour slowly, and I rotate the flask as I pour to create a tortured path for any water. The water will adhere to the glassware slightly. Ooh, almost lost a drop of water there. I'm going to leave that back behind. Now there's a little bit of water that's off camera. There's a little bit of water that's in the flask right there at the bottom. Hard to see. And there's droplets of water sticking to it, adhering to it. This flask has no water adhering to it. You can see as I swirl it, the flask doesn't even look wet. That's what a dry flask looks like. This is now ready for mag sulfate. Okay, I'm going to try and show you the mag sulfate step. So I've got this zoomed in. And the idea behind the mag sulfate is when mag sulfate is anhydrous, it's a powder. And so what we've got is we've got a white powder that I'm going to introduce into the flask. And that white powder, as it goes in, as it clumps, the clumping that we see is because it's absorbing water. And yet, when we swirl it, what we're looking to see is there material that kicks up into it that sort of snow globes? And as long as there's material that is free-flowing, that kicks up into it that is snow globing, well then that's really what I'm after. And that's all I need to see. And that's what I effectively have inside this flask is a little bit of free-flowing powder that when I swirl it, it all kicks up, and then it all coalesces and settles down. That's what I need to see, and that makes for a dry solvent system that we've got there. All right, the next step with this is to tear a round bottom, decant it into the round bottom, and then we're over at the rotovap. We're back over at the balance. I've got a round bottom flask on the balance, and we're just going to get that mass real quick. So we're reading 18.022, let's call it 1/8. Okay, we're over at the fume hood, and we've got one decant step to do. We want to take and put the contents of the flask into the round bottom to be able to go through and do the rotovap. So what I'm going to do is I'm going to decant the Erlenmeyer flask, and I'm going to do it in such a way as to try to keep all of the magnesium sulfate in the flask. You have to commit to pouring. Pour quickly enough so that it doesn't spill down the back side. A little bit of rotation. And we're done. You can see that we've retained the mag sulfate, and we have not gotten any mag sulfate into our round bottom flask. All right, we'll put the lid on this. We'll put it into secondary containment. We'll get a label on it, and we will meet back at the rotovap. All right, what we're looking at here is the rotovap, a rotary evaporator. And its entire purpose, what it's designed for, is to evaporate solvents really fast and to recover those solvents. It works in three ways. Number one, it has a heated tank. So what's going to happen is the round bottom is going to go into this tank. It's going to get heated. That's going to cause faster evaporation. The round bottom hooks onto this piece called a bump trap. This piece gets rotated. The rotation increases surface area. When you increase surface area, you increase evaporation. And then there's one other part over here. That's this guy over here, which is a vacuum pump. Now this is a water aspirator. It works by pumping water past a small aperture, a small hole. When water flows past it, by venturi, it sucks in air. The air that it sucks in is drawn through these tubes. These tubes connect here to the top of the rotovap. That reduces the pressure in the rotovap, and I can control how strong that pressure gets by a small valve up here. Controlling that pressure then, I reduce the pressure, that increases evaporation. You have to play with all three variables to get it just right so that you evaporate without fast boiling. We just want fast evaporation, not fast boiling. The solvent recovery component happens by taking an ice bucket, ice water, cold water, circulating it through a condenser that is up in this part. Hot vapors will travel through the device up into the condenser. They will hit that condenser, they will fall down into a reservoir. That reservoir then sits in ice water and captures it so it can't re-evaporate. So it's for both evaporation and recovery of the solvent. Let's see it in action. All right, so that's as long as it took. We evaporated all the solvent off the crude triphenylmethanol. Take this guy off. We'll dry off the round bottom. We'll get a weight. We'll figure out how much we got in terms of the crude product. Okay, now it's important every time we get a solid, it's important that every time we get a solid, we weigh that solid. And so we've got a solid here that we've isolated, which is our crude triphenylmethanol. And we're going to weigh it real quick. I want to show you what it looks like, though. Let me show and see if I can get it into the camera view. It is an off yellow material or off white material. I've scraped it down in the round bottom a little bit. It's probably still really heavy with solvent. We're going to see. We're going to put it on the balance. We've tared the balance already. Now, round bottoms are tricky because you can't lay them down anyway. So one thing that I do when I have a solid in a round bottom, which is a nice convenient thing to do, is I use the same lid and just set the lid down to use as a little holder, essentially. And let's get this mass. All right, we've got 19, 5, 4, 3, and we'll let it settle. And it may not settle because it's still got a little bit of diethyl ether in it after coming off the rotovap. It hasn't fully dried. Let's take it. Ooh, that was so close. No, it's just going to keep going. So you know what we're going to do? We're going to call it 19.542 because it's probably going to settle like around there. Or even if we just call it 19.54 for right now, and that's going to be fine. 19.54. We don't need all the rest of the sig figs. It's just to get an idea of how much mass is there. And we're going to go and we're going to triturate this next. So we're going to write it down in the lab notebook as 19.54 grams. All right, we're back here at the hot plate, and we're going to do this trituration step. And the trituration step is where we wash it with petroleum ether. So what I've got is I've got the bottle of petroleum ether, and usually I would just get a smaller amount, but 3 mils we can transfer here pretty quickly. So that'll be 1, and I'm going to rinse it down the sidewalls of the round bottom. Trying to rinse everything down. Into the round bottom itself. That was 2, this will be the third one. And what I'm also going to do, so we've got a secondary containment for our pipette there, is I'm going to throw a spin vane in this. Now the book doesn't say to do this, but throwing the spin vane in there is helpful in that it's going to kick the solid around and break the solid up. And as it does that, it's going to triturate it. So the idea here is that we want to wash all of the impurities out of our solid. Our solid is triphenylmethanol. It is more polar than the benzophenone, the bromobenzene, any benzene that might have been made, any biphenyl that might have been made. All of those things that could be in here are less polar than the triphenylmethanol. They are going to dissolve in the non-polar petroleum ether, and then we're going to filter them. So we're going to let it go like this. I'm going to give it just a little bit of heat, just to warm it up. I don't want to boil it or do anything like that. And then we'll take it off of this, we'll ice it for a little bit, and then we'll filter it. And I'll show you that filter setup. All right, I thought I might show you how I build this filtration apparatus, the whole setup for filtration. It's a little bit complicated. It's not going to be a good angle to actually see how this all goes together, but I'll walk you through it as I'm building it, and then I'll take the camera and show you what it looks like, what we've got here. So the parts. We have a very large 3-prong clamp. That clamp hangs on to a vacuum trap. This is a trap that is both for liquids and for anything that is fairly volatile that can be condensed. So hopefully any of the gases that make it through that can be condensed are going to get trapped in here. We're going to set this trap down into an ice bath and wiggle it into the ice bath so that it sets in there a little bit and lock it into place. We're going to use a smaller 3-prong clamp, just like we used for our chemical reactions. That piece is going to hold on to a sidearm flask. This is a sidearm Erlenmeyer flask. We'll lower it down so that it's not too high up in the air. These two, the flask, the sidearm flask, and the filter trap, get connected with strong, heavy-walled vacuum tubing. And we connect them in a nice U so that there's no tension between the pieces. The other side over here connects to the vacuum that is the house vac that is down in the basement. And then once everything's in place, then we take the actual funnel, which is the Hirsch funnel, and put the Hirsch funnel in, and there's a little piece of paper inside the Hirsch funnel. That's it. Our apparatus is set up. We're ready to do our filtration. Let me take the camera and see if I can show you what this actually looks like. All right. So what we've got here is we've got the vacuum trap here, and it's actually in the wrong position. Now that I got down close enough to be able to see it, it's in backwards. There's a short tube. This one is short. This tube is long. What you want, ideally, is you want the outflow coming out of your filter apparatus to go into the long tube so that the vapors get deposited at the bottom where the water ice bath is. That will condense them back into liquid, preventing them from making it back up to here, which should be the exit going to the vacuum itself. So we're going to take a second. We're going to turn this around. Good thing I showed you that, because I might have missed it. Now these tubes don't need to go on to these glass pieces very far. They just kind of go on and push on maybe 1/4 of an inch, if that. And just a little bit of twisting, and that's it. That's all they really need. And you always want to support the glassware when you're putting these on so that it doesn't break. That's the whole thing. All right, now we should be in place. Our stopper is closed. Everything's good. All right, and I'll show you real quick the Hirsch funnel. The way that the Hirsch funnel works is the Hirsch funnel has a little piece of paper in it, and there's holes underneath. The paper fits over the holes to be able to trap your product. We'll moisten that just before we run the whole thing. And then this here is a pressure relief valve, so that when we're done, we can let the pressure out. Normally, vacuum builds up into this, and your product is sitting on here, and if you try to take the funnel off without releasing the vacuum, the funnel won't come off. And then all of a sudden, you'll apply more force, and it does come off, and your product goes flying as you get surprised. Okay. Let's take a look and see how our trituration is going. All right, we're back here at the trituration, and it's warmed up now, and it's as warm as I want it to get, which is not very warm because petroleum ether has a boiling point which is right around 34 to 37 degrees Celsius, so I don't want to boil it, Just wanted to warm it gently. And what I want to do is I want to turn off the stirring and let it settle. And I think that what you can see as it settles, see down here on the bottom, I'm using a pipette as a pointer, see the white solid on the bottom? And see the liquid sitting on top? All right, the liquid has taken all that yellow color. It has picked up all the contaminants, and the contaminants are what are in that yellow color. Our triphenylmethanol is white. The trituration has done its job. We're going to go filter it. We should receive a white powder on the filtration apparatus, and what we'll do is we'll filter it, and then we'll rinse it just with a little bit of petroleum ether to rinse any of those impurities out. And that should be it. Okay, I iced it down for a little bit, and I wanted to do that because we're trying to get as good a yield as we can here. And we really don't want to lose material by not keeping the solvent cold enough. We'll get our vacuum on, make sure our paper is sucked down well, upend it fairly quickly, and then we will drag it out using a curved spatula, releasing out all the solid that we can. Let's see if I can show you what I'm doing. And it's just a little bit of patience here in scraping all the material out. Alright, I'm going to do a little bit more work on this. I'm going to get ready to rinse it, and then I'll show you what we've got. Alright, I'm going to try and show you what the product looks like here. Let's see what happens. Alright, I think you can see there that we've got a pretty good solid material. It's a little off-white still, but pretty darn good. And it's been sitting on the filter for about 5 minutes, and I've been stirring it every now and then just to get some air through it. And the idea there is that we're just trying to evaporate as much of that petroleum ether as we can before we go and weigh it. And we may not get a good weight on it today. We might have to weigh it again in our next lab in order to have all that petroleum ether really evaporate and get a good solid mass. But we'll get a mass today, we'll get an idea of what it's going to weigh before we move forward with it and do our melting points and our spectroscopy. All right, what I've got is a petri dish. I've labeled it triphenylmethanol. We're going to get a tare weight on it. Then we're going to take the material out of the funnel, put it in the petri dish, and we'll get a mass today. .81768. And it moved on me after I took it. I'll show you. Okay, a little word about this analytical balance. This guy is fussy. Okay, so it is weighing out to 1, 2, 3, 4, 5 decimal places. This thing could weigh your fingerprints. Breathe on it wrong. Step on the floor wrong. Right on the table while it's trying to balance. It is that sensitive, it will throw it off. 80.81753, that's what I'm going to record. Done deal. Alright, this is taking the material out of the Hirsch funnel. Now, we've got the paper and we've got the spin vane to worry about. We've got to get both those items out. and there's a good amount of material adhered to the sidewalls. And so you just want to be systematic and make sure that you're policing and getting all that you can. Every time I go to set it down, I see a little bit more. Okay, now regarding the paper, what we want to do with the paper is we want to dislodge any solid, but not scrape so much that we start removing paper fiber. So we scrape it lightly, and it's best if the paper is drier before we go too far with that, because the wet filter paper really tears easily. And that's when you get more fiber stuck into your product, which we're trying not to do. That'll show up in our spectroscopy. It'll show up in our melting points if we're not careful. Okay. And the solid, rather than leaving it in big clumps, you want to spread it out. Spreading it out gives it more surface area, more higher evaporation rate in order to get all of that solvent out of it. So that's what we'll do here for a second. We'll just take and spread it around. Any big clumps we break up, and just give them some more surface area. All right, time to go get a mass and see what it weighs. Back at the balance, we have our triphenylmethanol. The balance is zeroed. Let's see what we've got. $81.879. We'll wait for it to stabilize. We'll stop moving. We'll stop moving on the floor. Here we go. 81.88003.